calibrated to a known force. So what we do is we put a strain gauge in here and we apply a known force. So let's say we put in 100 newtons of force, and we push down. We would get a certain amount of strain and we'll get a certain amount of change in our resistor. Then we will write that, we'll create an XY chart, the X there and the Y there, and we'll mark our first, and X will be force and Y will be displacement, or delta. So F and D. So you go over here to 100 and you get some amount of displacement, or I should call this, we'll just call it voltage. Doesn't really matter. And then we apply 200 newtons and we get another, and so on until we get a chart. And that chart might be linear, but it also could be curved. It doesn't really matter too much, as long as the more we do this, the better our curve fit will be. So if we do this a whole bunch of times at various weights, so let's say 10, 100, 200, 500, whatever, so on, we can get a nice chart here that we can use as our model for our strain gauge, for our power meter. Okay, so that is how you get that's how you get to know what the forces are, because you've created a little circuit that will tell you, because you've done some you've pre-tested the system. All right, so that's the Wheatstone Bridge. I guess that kind of can get rid of that now. We now understand that. We know how this works. Okay, so that gives us the unit of, so now we know what force is, and work is equal to force times the distance. So we know force. Now we need distance. Okay, well, the distance is basically the length of that the force is working in. Now most people know that when you put force on a pedal, you don't get to put the force all the way through a full pedal cycle. You have what's called a power stroke. So if you look at the pedal motion, it starts up here at 12 o'clock. It's rotating down through to 3 o'clock, and then down to 6 o'clock, and then 9 o'clock, and so on. And it's moving through this circular pattern. What's interesting is that you definitely are kind of no longer applying pressure down here. In fact, you're actually trying to lift up on it, or even you're actually pushing backwards on it in some cases, because your foot, the weight of your foot is on the pedal. So this is where you're not applying in these quadrants. Call this 1, 2, 3, and 4. In quadrant 1 and 4, you're really not applying any power. You're actually probably taking some power back. So your power stroke is on this side only. So your force is going through the arc from 12 o'clock to 6 o'clock. And so therefore, when we get a power number from our little Garmin, instantaneous power will change, because right here the amount of force on the pedals is basically, so here's where we can talk a bit about instantaneous versus average power. So if you were to look at the force here, it's almost 0, and if you look at the force here, it's at its maximum, and then down here it's at 0 again. So the force kind of, if you plotted force over time, you might see a chart that looks like this, right? Because your force is 0 here, and it starts to build up to here, and then it decreases down again. So your chart might look something like that, your power over this 1/2 of a cycle. And so instantaneous power are these powers along this curve at any period of time, instantaneous period of time. Whereas average power just says, okay, let's look at a much larger period of time. Let's look at, say, 5 rotations of the crank. And if you take 5 of these and you add them up and divide by 5, that would give you 5 that would give you the average power over 5 cycles. So average power is just taking the instantaneous power and dividing it over some period of time. All right, so that's how that works. So I showed you how the strain gauge works. I showed you the distance is the force. The distance that the force is traveling through is just the length of the crank arm. And the other thing is time. Well, what is time? Time is actually your cadence, because what it is we're looking at each revolution of the crank arm. So if you're riding at 60 RPM, then your time would be 60 cycles per second or per minute. And if you're looking at, which I don't recommend, by the way, so the average cyclist kind of pedals in an 80 to 100 RPM range, which is a good range to kind of stick to. But you could drop down to 50, 60, or 50. I mean, some people ride at lower cadences. Either way, we're measuring time with our little magnet here that's going around with the crank arm, and it's getting picked up by a sensor somewhere on your chainstay, usually. So that can measure time, and that number can then just be put right into this equation. And the distance is this length here, and that has to be programmed into the computer so that it knows whether you're using a 175 millimeter crank, a 172.5, and so on. There's different lengths of cranks available, so that just needs to be able to be programmed in so that you get a more accurate reading. Okay, so now we were able to see that there's two variables here. One is the amount of force, and the other one is the time. And we can talk a little more about that and how you can increase power by increasing cadence, and you can decrease power by you can increase power by increasing your force. So you have two ways. So yeah, let's take a quick look at how that works. So now you see how the time aspect works. If to increase the power, you can increase work or decrease the time, right? So decreasing the time is increasing the cadence, because as you increase cadence, the number in the denominator gets smaller, see, because it's happening every revolution. Remember, the force is being applied at every revolution. So therefore, there's two ways to increase power. One is through strength training, and one is through cardiovascular training. So having an ability to spin at a higher cadence means that you will create the same or more power and possibly be more efficient. Okay, so I think that gives you now enough information to understand the differences between instantaneous power and average power, and how power is measured. And I also gave you a little insight into how you can increase your power by increasing cadence. And if you can also, and actually your crank length actually plays into this a bit too, because remember, work, if we remember, is force times distance. So for a longer crank arm, you would get more work done with the same amount of force applied. So by putting a longer crank actually on a bike, you can increase the power. But the problem is, when you're looking at the time aspect, remember, is that the pedal has to go through a complete circle. So if the circle is to increase in diameter slightly because you have a bigger crank arm, so let's call this crank arm 1 and crank arm 2, so 1 and 2. If you increase the length of the crank arm, then that particle, if you will, will take longer to traverse the full circle. And remember, there's this part of the equation, time. So there's a point of diminishing returns. So really with a bicycle and with power, you're trying to be the most efficient you can. And so you need to find a proper crank length that matches you and your abilities to spin at a certain cadence. And cadence can be trained, and power can be, and force can be trained to a certain point. And then there's these other things that can be done to help improve your own efficiency. Anyway, I don't want to get too much into that. I think maybe that would be another good, that might be something for another video. So anyway, I hope you found this to be interesting, and feel free to leave some questions in the comments. And if there's something I left out or if I made a mistake on, feel free to correct me. And that's all for now. Hey, so after I finished editing this video, I realized I failed to mention why I brought up the Wheatstone Bridge in the first place. And that is simply because a Wheatstone Bridge is a fancy circuit that allows you to wire in a second strain gauge that can be used to measure the changes in the material due to outside temperature changes. So remember, metals expand when they heat up and they shrink when they cool down. And if there wasn't a temperature compensating strain gauge in there, the reading that is sent to the Garmin or whatever your bicycle computer is would not be compensated for those changes due to outside air temperature. Now, that doesn't seem like it would be a lot, but because the amount of strain due to the forces of a human are so small, they're actually in magnitude very comparable to the strains that would occur due to changes in temperature. So a Wheatstone Bridge provides you with the necessary circuitry to essentially compensate for the outside air temperature, and that is why I mentioned the Wheatstone Bridge to begin with. Anyway, if you have any questions, feel free to post those in the comments section, and I will do my best to try to answer them if I can. Thanks for watching.